So, according to the Barminster theory, Barminster theory, for rigid plate 1.5 Pa by Es into F2 delta equal to delta is design deflection, P is the contact pressure, at road surface, A is the radius of contact area, E is the modulus of elasticity of subgrid, F2 is the deflection factor based on Es by Ep and H by A. H thickness So, for flexible pavement, 1.5 Pa by Es into F2. F2 is the factor of Es by Ep, comma H by A. H is the thickness of reinforcing layer. Delta is design deflection for rigid pavement 1.18 Pa by Es into F2 is a function of Es by Ep, comma H by A. Now come to the rigid pavement. What are the factors? There is various factors: wheel loads and its repetition, area of the contact area, location of the load with respect to the slab, properties of the concrete, strength and Poisson ratio of fatigue, modulus of elasticity and shrinkage properties, and temperature and frictions, and joint, the spacing of joints and arrangement of joints, and the type of reinforcement. Those are the factors. So, what are the factors? Factors for design of rigid pavement. So, design of a rigid pavement is equal to function of wheel load, repetition, area, location, temperature, subgrade strength. Modulus of elasticity of the subgrade, shrinkage properties, temperature, friction, arrangement of joint, spacing of joint, quality of reinforcement, etc. So, wheel load, repetition, area, contact area, that means location, modulus of elasticity of subgrade, shrinkage, temperature, joints, spacing, all are the factors that are responsible for design of rigid pavement. So, what is rigid pavement? The rigid pavement is basically this is cement concrete slab, and this is subgrade. No, 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 no. This is the base, and this is the subgrade. So, three layers exist. The first is slab, and other is base course, and third is subgrade. So there are certain assumptions of Westergaard for design of rigid pavement. The concrete slab is homogeneous, isotropic, and uniform elastic properties. The load at interior and corner is circular in shape and edge is semicircular. So modulus of subgrade reaction is calculated by delta. Delta is 0.125 centimeter, that is taken by 75 centimeter plate. If there is any other plate is used to calculate, then take we have to calculate it these reflections for 75 plate. So to calculate the relative stiffness of the slab of the subgrade, to radius of relative stiffness, radius of relative stiffness is measured by EHQ bar K into 1 minus mu square whole to the power 1 by 4, E equal to 3.0 into 10 to the power 5 kg per centimeter square. H is slab thickness in centimeter. Mu is equal to 0.15 concrete, and K is modulus of subgrade reaction. So suppose compute the relative radius of relative stiffness if h, that means slab thickness, is 20 centimeter, E equal to 2.1 into 10 to the power 5 kg per centimeter square. K is subgrade reaction is not known, and mu Poisson ratio of concrete is 0.15. The K we have to calculate is P by delta, that means P by 0.125. P is equal to the load is 2000 kg, so 2000 kg divided by pi by 4 into 75 square is equal to 0.453 kg per centimeter square. So K is equal to 0.453 divided by 0.125 is equal to 3.62 kg per cm cube. So L is equal to 79.31 centimeter. So we have before the at the earlier stages of this chapter, there we have already studied that at the interior and corner the pressure is circular, and at the edges the pressure is semi circular. So suppose this is the plate, this is the interior portion, and this is the interior portion, and this is the edge portion, and this part is the corner portion. So we have to calculate what we need. We have to calculate the radius of relative stiffness of at this location, at this location. So equivalent resistance, equivalent radius of resisting slab is B is equal to 1.6 a square plus h square minus 0.675 h. This condition is when a is equal to 1.724 h and b equal to a when a greater than 1.724 h. A is the radius of wheel load. So A by H equal to, suppose in a problem, A is equal to contact area, that means pi by 4 into A square is equal to 707 A square is equal to 4 by pi into 707. A is equal to 2 by root pi into 707 is equal to 15 centimeter. So 15 centimeter and 20 centimeter thick slab, that means 0.75, which is less than 1.724. So we have to calculate in this formula 1.6 a square plus h square minus 0.675 h is equal to 1.6 into 15 square plus 20 square minus 0.675 into 20 equal to 14.07 centimeter equivalent radius of resisting section. There are various formula available as per Westergaard formula at various position. Interior is equal to 0.316 p by h square 4 log 10 l by b plus 1.06069. At the exterior portion, 0.572 p by h square 4 log 10 l by b plus 0.359, and corner region 3p by h square bracket the 1 minus a root 2 by l whole to the power 0.6. H is centimeter, it is slab thickness. P is the wheel load in kg. delta A is the radius of wheel load distribution. Temperature stress is due to daily variation and seasonal variation is equal to E alpha T by 2 Cx plus mu Cy divided by 1 minus mu square St is equal to Cx alpha T by 2 comma Cy E alpha T by 2. This will be minimum of, and STC is equal to E alpha T divided by 3 into 1 minus mu in bracket A by L. E is E is 3 into 10 to the power 5 kg per centimeter square. Elasticity of concrete alpha is 1 into 10 to the power minus 7 per degree Celsius. T delta T temperature difference. The frictional resistance formula is F is equal to FWL divided by 2 into 10 to the power 4. So, if the load at interior portion so this is the previous condition of the road after deflection, it will be like this. It will be like this, and P is the applied load when applied at the edges. Ah, so let us come to the warping stress. Before come to the warping stress, let us discuss about stress. It is the reaction. So suppose this is the road, this is the subgrade. At the daytime, the upper portion is hit more than lower portion. So upper portion get elongated. That's why the resisting section is in compression. The resisting stress is compression and the lower portion is tension. At daytime, at night time, the environment is all already heated. So this will be the bending profile and this portion is try to elongate. That's why this is in compression and this is tension. So let us divide various conditions according to the daytime and night time. The location at interior portion, load stress, warping stress, daytime, night time, and frictional, summer, winter. So at the interior, the top and bottom. At the daytime, the top portion is in compression and bottom portion is tension. And at the night time, top portion is the tension, bottom portion is compression. The top portion is compression, bottom portion is tension. And the friction and at the edges, compression top at top and bottom. So the critical stress at summer is equal to S critical is equal to SE plus SF minus SF at winter SE plus STE plus ST. So at summer, at winter, SE ST minus SF, the winter SE plus SF plus ST